Right, hello everyone. Welcome. How's everyone doing? Hey there, Ansel. How are you? I'm just gonna get the chat up on my phone. But yeah, sorry, I've just been attending to the grass outside. How's everyone's week been so far? Right. Just getting the chat up now. Cool. There we go. Much better. Doing good? Yeah, not doing bad. Oh, it's been super busy. Busy weekend, also very warm weekend. Very jam-packed. So, there we go. So last stream, we got the GPU API complete, right? So this whole sort of GPU.h is now finished to a reasonable degree. Obviously, there's some the C code behind this has to definitely get corrected as we build more features into this sort of game project. But the core of it is here, just has to be fixed up, and we have to maybe complete things to make it maybe work across more platforms. But yeah, we have a way to create buffers and textures, upload to those buffers or textures, read back from those buffers or textures, and also launch some compute shaders, right? So with that, effectively, we get this here. Oh. So now we kind of started this project doing the GPU side of things first because it was the most complicated part of the engine, right? Even though we're not making an engine, right? The engine of the game. It was the most complex part that we wanted to do in a very simple way. So we've done that now. So now we want to build the rest of the engine. Hey there, Perry. Yeah, not doing bad. We're doing quite good. We're getting close. Like there's literally like 1 month left now to the baby. So this week is my wife's last week at work, and yeah, then she'll be off, and then I'll be off whenever the baby comes. So yeah, things are definitely getting close. Hey, not so red. How you doing? How's things been, Perry? You doing good? It's been super warm. I've been like surviving off these things, you know. Hey there, Nico. Hey there. Nice. Good to hear, Perry. Back to the Pepsi. Yep. I'm drinking like two or three of these at the moment because it's so warm. It's not good. It's so nice and refreshing, you know. But yeah. Right. So the plan is you want to iron out some parts of the engine. So I did. Well, I keep using the word engine, but we're not making an engine. So I did on my Discord post kind of what we want to be doing, and obviously it's in the title, right? But here's the plan. We're going to do some virtual memory. We're going to talk about what virtual memory is, go over how it works in a way, and we're going to implement it, and probably talk about the pros and cons of virtual memory, like where you might want to use it and where you might not want to use it. What projects you want to use it and what projects you don't. We want to make our own stack and a hash table and object pool. hook in some keyboard and gamepad input. We want to be able to hot code reload both CPU and GPU code. And then obviously, so this is like the engine part I'm talking about. This is the stuff we've not been doing. So anything after here is kind of like using the engine we've built, right? Or the core of the game, shall we say. Awesome. So I can close these tabs here because these are Vulkan. We're not doing Vulkan no more. No. None of those, please. Yeah, hot code reloading, it'll be fun. It will have some slight issues, but I think we'll be able to work around them. Growth in common list. Ooh. Great. Then everything has to be pure. Pure functions, my favorite. So we have in the source directory an OS folder. And this is where we want to be putting our virtual memory stuff. So what is virtual memory and why do we need it? So when you allocate anything using C, typically people will just use malloc, right? So go into like a C file somewhere. Typically people will use malloc. So they'll be like, hey, malloc 8 bytes, and then they'll get back a pointer to something. So maybe you have an int star as an example array, and you might say I want 8 times size of int. And this is how people typically allocate memory, but this is not how memory actually works under the hood. How it works on every operating system is by using this concept called virtual memory. So yeah, effectively on every modern operating system, but probably not on embedded, and definitely not on in a new platform called WebAssembly. Yeah, so this is some of the issues with it. So I think what we'll do is we'll speak about what virtual memory is, and then we'll go into the pros and cons of it, and then we'll talk about the platform abstraction we'll have. So, right, I think a good place to demo this is like Godbolt, I reckon. So if you notice when you print it, so I think like it's probably easy just to say, if you think of a pointer, if you think of a pointer, so you have like a char star, very terrible handwriting. You know what? You have your pointer, right? And it points to. So imagine this is all of your RAM. You know what? I'm not going to try and write stuff. This is all of your RAM here. Now, if you have a pointer, it will point to a location in memory, right? But this is kind of a lie. There's actually steps in between this, and it's quite easy to see it. So we just print out P. So this is name. So what does name point to? Yeah, let's avoid writing stuff. It's so hard to draw because I'm using like this vertical mouse here, and yeah, it's not easy to. I can't master my vertical mouse. Yeah, here we go. Master and C pointers. Exactly. Hey there, Glass. How you doing? How's things going? Right. So if you see the console output, where's the executor? There we go. Right. So say if we have like let's try that, shall we? Right, so maybe that's not a good idea. Maybe we should use malloc. This is not illustrating what I want to illustrate. And this one needs to go up here so you guys can actually see it. Maybe we should use malloc. Standard lib. It's not illustrating what I want. There we go. That's what I want. So we have a pointer to test, right? And here's the pointer. Look how big that thing is. So this clearly will go outside of you know, I'm not sure how big this number is, but it's definitely over like gigs, I reckon. Let's figure this out. So 1, 2, 3, 4, 5, 6 bytes, right? So 6 bytes. So obviously 4 bytes is 4 gig, right? And then anything after that you start getting pretty huge. So this is clearly like, if you were to look at this graph here and say the pointer points to RAM, and imagine this RAM is 4 gigabytes, right? But we've just got a pointer which says 0x7fcb, whatever, and this is pointing like way outside this 4 gig boundary, probably like into the terabytes, right? And you're thinking, how is that even happening? Hey there, Igtis, how you doing? Oh no. Goodbye, glass. Awesome. So, right. So there's actually something that goes on in between when it comes to actually accessing physical memory. Effectively, if you take a look at your pointer, there's okay. What's the best way of saying this? So effectively, what you have is your operating system breaks memory down into pages, hence why you hear the word page size. So if you run it on like if you run it on Windows, it's probably, well, see, it's a bit different on Windows, but yeah. So typically the page size is like 4K, right? If you run this on Mac or Linux, it's 4K in size, from what I remember. And effectively, the operating system breaks memory up into these page sizes. And what it does is, when you have a pointer, what's a good way of saying this? So you effectively, with virtual memory, you have the entire, well, maybe not the entire 8 bytes. I think on some operating systems it's 56 bits of address space, meaning you can have a number which maps into all the way from 0 all the way up to like so many petabytes. And if you were to access anything within that range, it's going to essentially look up to see whether that page has been either allocated or it's not been allocated. If it hasn't been allocated, you get a seg fault, and that's where the signal comes from, where you can get a seg fault. It's because you're trying to read into some page that has not been allocated. So from zero, so from zero, there is a whole page which is known as like the null page, and on some operating systems this can't be actually be made into a proper page and be used, because if you were to add to this pointer, it means that you still get a hex fault, and then the system will still crash, right? As opposed to you like adding 1 to this pointer which is 0 and then it working, right? It's just to catch those sort of problems easier. So imagine after 1 you've got this next page which starts at 4K. You could probably allocate this on systems, but I've not bothered trying. But this page, so this a pointer that points to 0 will be within this page, and maybe you have the physical memory up here. And so say if we want to, say if our pointer points into here, so it's got like an address of 2048 or whatever. What it's going to do is it's going to figure out where is this page in memory, and it might be like all the way up here for some reason, right? Maybe this is like 2K. Yeah, maybe there's like 2 gigs of memory in here, and perhaps that 4K just like lives at the top end. And then if you have a pointer into this place in memory, which starts at 4K in your program's virtual address space, right? And maybe this maps to some physical memory over here, right? So what's quite interesting is your program has its own address space that doesn't overlap with any other program, and you can sort of allocate these pages and deallocate these pages within your programs within your program, and no other program can access it unless it's like a child of the program you specifically give it permissions. So one advantage of this virtual memory system is security, meaning a program just cannot sweep over the physical memory and read that. It has to access it through this virtual memory system, and it can only access it providing it has the permissions or a mapped page to that physical memory, right? Mapped is the word, that's it. So when you ask the operating system, when you use virtual memory to like reserve and then commit some virtual memory, it can give you anything within from 0 all the way up to like 6 or 56 bits. So it's all the way into the petabytes. And it'll just give you a group of pages rounded up to the nearest of 4K, for instance, which is the page size. And those can all be either linear in physical memory, or they could be broken up into different 4K segments. So another pro of this is you could have I don't know why I undid all that. Yeah, you could have these supposedly contiguous in virtual address space, but they're actually broken up into different places in physical memory, thus reducing actual fragmentation that goes on, right? Is the OS abstraction / software powered mechanism, or is it hardware built in structures through functionality for this? Yeah, it's hardware based. Yeah, so that's the next thing to get into as well, is page tables and translation. Yeah. So what other benefits does it bring? Right, another benefit that it brings before we get into that translation table stuff is because the operating system gives you back a page of memory, you might be like, hey, I can now finally read the contents of the memory that was there from some other application, and maybe like spy on some other application somehow. But so how like an operating system fixes this is they literally give you back a zeroed page. So whenever you map a new page into memory, maybe this is at like just somewhere like completely far off into the distance, and this maybe maps this guy here. As soon as it maps it, the whole piece of memory within here is completely zeroed. So that's done for like a security reason, but also it can be used as a programmer. Like, maybe if we can assume our data is zeroed, that could be the way our structures is. We could like, maybe all of our state for our game can start off just by being initialized to 0, and then that's like that's always a known state that we can rely on. So maybe like having our pointers are 0, right? The size of arrays typically start off at 0, right? So it's a safe state, which means it is initialized, and our program won't do random things if we were to just start using this data. It would maybe crash in a graceful way, or maybe you can start off from 0 safely, right? So this is something else to keep an eye of. So unlike using this function here, unlike using the built-in C function, so imagine you have a string equal malloc, maybe like, I don't know, 10 bytes or whatever. The way it's written is that the memory is uninitialized. So it could be all zeros, right? But the spec says that it is uninitialized, because you could free something and then allocate it again, and it's just giving you some old data that your application has messed with. And obviously there is a function called calloc, right? And this one like purposely like will actually go over and do like a mem set over the memory, but yeah, it's not the same as virtual memory, at least. Okay, I'm not sure there's much else to. So, I think it's safe to say there is some more advanced tricks you can do with virtual memory, but we're not going to cover those today, because we're just going to cover like what virtual memory is and what is the core of it, and how we can use it as well in our engine. Can different parts of one physical block be allocated by separate? Can one parts of the physical block be allocated by separate programs? Yes. So say if I were to have, say if this is my process, right? And I just have a child process, and say if my parent process allocated this like this page is in virtual memory. You can set some special permissions to say like, I think it's when you create. I'm not sure exactly when it is, but maybe it's when you create the process, or maybe it's. I think maybe when you create the process, you can maybe say all of the virtual memory pages are visible, or maybe you can only make some of them visible. But yeah, you have to. I think you have to share it with a parent-child relationship with your processes. Like the parent has to launch the child process, from what I know. Oh, they don't need to be parent or child, right? I wonder how you'd do that then. There must be. Right. But yeah, I'm not quite familiar with that one. But yeah, it is possible, but you can't. Yeah. Because it would be a security problem if another program could just look at your mapped pages, right? Or just use your mapped pages. Yeah, it was a System 5 SHM thing. Yeah, I'm not too familiar with that though. Hmm. But yeah, I know you can use that to do some advanced stuff with it. Right. So I guess the question that would probably be going through people's heads is like, so with all this stuff going on, surely this is dead slow, and without this system, it would like hardware would be so much quicker. Um, so I've not done any benchmarks in what it's like to turn this thing off, but how computers get around this problem is they actually have a special piece of hardware called the MMU, and it's called the Memory Management Unit, right? And they also have a thing called a TLB, which stands for Translation Look-Aside Buffer. So I'm not sure on the exact specifics here, but we can sort of just give a general idea on how this thing works, and you can go and do your own research from this. Yes. So effectively, remember we said our page size was 4K on, it's 4K on most operating systems, but on Windows it's a little bit different, and we'll get into that when we write the implementation. But yeah, 4K basically. So with a 4K page size, you can fit that in the first 12 bits of the address, right? So that means so wait, what is 12 bits? You've got 4, 8, 12, and there. Those first three. Whoa, ho, ho, hey there, Toggle. How you guys doing? Thank you so much for the raid. Appreciate it. How you been? How's the projects going? Hey there, Temporus. Welcome, Raiders. All right, jump into the sea. Enjoy, Toggle. Thank you so much. Appreciate it. I'll see you. Catch you soon. Have a good rest of your day. Welcome, everybody. So we're working on a game from scratch using nothing but C and our own custom C compiler for shaders. So we're currently writing our game without an engine. We currently have a GPU implementation. This is some data that's being printed back by the GPU to the C and given back to the CPU and then printed out into the terminal, so we can print from shader code basically. So we've got the core GPU system set up. So we're working on some more engine parts. So today we're doing virtual memory. We're learning about virtual memory and going to implement that system in. So the very low level system to do with actually allocating some memory from the operating system. But yeah, if anyone's got any questions about the project, feel free to ask and I'll happily answer that sort of stuff. Yeah. No, I don't have a shader toy account. Vulkan, 1K to draw a triangle thingy. Right, no, we're not drawing. Yeah, this is not really a triangle. We're doing it in pure compute. So this was just a bit of a laugh doing a triangle in a compute shader. But yeah, we're not doing a traditional triangle pipeline. We're going to try and do graphics in pure compute, and keep things really simple. So this is the idea with this. This is the idea with this game without an engine. We just want to try and do something in a very simple way, and try not to overcomplicate things, and do something more specialized towards this specific game that we're going to be writing. But we are writing the initial part, like the core foundation of the game, essentially the engine part, right? So we're just getting all the essentials to rapidly prototype something, and then do some good stuff. Is that UV map? No, it's just a compute shader. So I'll just give you a show, right? So here's our C file with our shaders in it. So this is ran for our custom C compiler HCC. And essentially we've got, where is it? There we go. We clear the screen to some gradient. That's all it is. It just takes the XY, divides it by the screen width and height, which is hard coded. Great. Yeah, and then it stores it out into the texture. What's the idea for this game? There's no idea just yet. We want to try and prototype an initial art design. So we want to come up with some art style which is kind of unique and not using the traditional rendering pipeline, just using compute shaders only. And it will be 3D. We just want to try and figure out like what that is first before I go ahead and say, I want to make this game. So I want to have that come into the process of coming up for a game design. Yep. But yeah. All right. So we was just talking about virtual memory. So we just spoke about how essentially every program has its own virtual memory address space. Yeah, I have my own compiler. It's for shaders, shader programming. So we compile our C code into SPIR-V, and then we run that through Vulkan, and we get to run C code on the GPU. It's got some restrictions. I'll drop a link in the chat. Wait a minute, which one am I going to? That one. This one. Check it out here. There's some samples and everything there. It's got some releases. Yeah, there's samples, and you can download and have a play. Runs on Windows and the open source operating systems too. Well, not all of them, just the Linuxes. Hey Davros, sort of hoping to make a low poly game and throw something neural, something over it. Yeah. Huh. That'd be interesting. Or maybe use the neural part of it, yeah. Yeah, it's probably, if you're like an indie dev, going low poly is definitely probably helpful to getting something done. Just Linux, exactly. I'd expect within a couple of years there will be AI tools that can low poly art into high poly. Potentially. Yeah. Obviously there'll be a lot of like room for it to go into different things. But yeah, I see what you're saying. It definitely can. Yeah. It's a bit like you have the flat. You have some examples of that already with flat 2D images where the AI sort of like, you can like overlay 2 snippets of images and get the AI to fill in the rest. So I'm sure there's something like that, right? Oh, awesome, you got a command, thank you. Nice one. Yeah, I need to do that. Right, so we just spoke about how with virtual memory, you have a whole 64, not really 64-bit, maybe 56-bit of address space, and it maps 4K pages into physical memory. And so every time you access a pointer in like the virtual address space, which is in every program by default, every program gets this. No program executes without this except for the kernel. And you go and you have to go and access. So whenever you access a pointer, it looks up your 4K of that 4K page and tries to find the physical address, so where it can actually read the data from, every single time you access a pointer. So you might be thinking, this is really slow. And the answer is, like, there's hardware to sort of make this as small of a cost as possible. So there's a MMU, which stands for Memory Management Unit, and this is what the operating system will use to set up the mapping, right? It will map this virtual address slot Oh, Sherlex, thank you so much. Appreciate that sub. You yeah, welcome to the club, my friend. Welcome, welcome. So, what's a good way to explain this? So, yeah, so the memory management unit will have essentially a lookup table in a sense to sort of translate it from your virtual address space to a physical page. Now, so remember when we said we have 4K 4K page sizes on pretty much most operating systems. Well, how these ones will typically work is the first 12 bits, right, will be the offset from the start of the page to where it is like inside the page, right? There's that. So that means the rest of the bits for the pointer can be used to go through this MMU and find like this physical address. So typically what it does, right? Okay. And there is like, this is definitely specific to an implementation. So I won't take this across all hardware. This is just what some implementations might do. And there are ways they also speed this up on top of this. So this is just a general idea of what goes on. So in the MMU, when you ask for a page, one thing it can be doing is there will essentially be an array of tons of entries. Maybe there might be like 12 bits of entries, right? So that's 4096 of entries. And so then they use the next 12 bits, for instance, to sort of map into this table, right? And to say if it maps to this guy, this one will then load up another, like each one of these has a table of their own. So there's a second level of a table, right? So imagine this one has a table all the way over here, and it's another 4,090 whatever entries, 96 entries, and this one is another table that has 4,096 entries, and there's levels of these tables. So they might go, right, so they access this table, then it uses the next 12 bits to access into this table. Maybe it takes this slot here, right? And then maybe there's even another level of tables, right? It could go through like 3 layers or something. And then eventually it uses the final 12 bits or whatever it is, right? This is just, again, completely hand wavy on how this works. Then this pointer here is finally the actual physical address, right? And then like this one gets pulled back. So we'll get like the proper address for these bits here, and then it will sort of add the offset into the page that we had all the way down here, right? To that final entry that it found all the way up here, right? So you might be thinking this is really slow. How many indirections is that? That's pretty slow. So typically what happens is you have this TLB, this translation look aside buffer, and this is where the most recent pointer reads will go into. It'll be a quicker way of doing this, basically. It's just a flat array or something. So it'd be like maybe like an L1 cache in a way where it's just super quick at getting that address which you've literally just looked at, right? Because if you were to write some code and you were to say, hey, I got this string here, I want to access string 0 and then write 1, 2, 3 into there. And then if I was to access string character or byte, the second byte, and then, well, okay, perhaps, yeah, okay, let's do that. And then say, right, like you'd have to go through that MMU twice, right? Just one after the other. So what the system will try and do is like cache that pointer that you've literally just looked at and put it in that TLB, so make it like a lot quicker to go and get that pointer. So again, this is very sort of hand wavy on how this works, but you sort of understand the idea is this whole system provides safety. It limits fragmentation because everything's split into 4K chunks that can sort of like intelligently allocate 4K chunks and sort of like free individual 4K chunks and allocate them. They're all fixed size, they're all the same, so you don't have to worry about having, you know, like, again, into fragmentation issues, basically. Yeah, there's also some other tricks that you can go into. Like, say if the operating system runs out of memory, it can be like, well, this page hasn't been accessed for a long time, so what I'm gonna do is I'm gonna write this out. I'm gonna page this out to disk, right? And it will copy it to disk. I'm not sure if our operating systems typically would do it too much nowadays with lots of RAM, but it might do in very stressful situations. But it could page it out to disk and then use this slot for another page that gets allocated by the operating system, by another program. And then when the other program that had this thing paged out tries to access this page that's on disk, the operating system will be like, hang on a minute. What I'll do is I'll allocate you a new slot now, and I'll read this page back in, and then I'll correct up with the MMU here and say, hey, this thing now points to here instead, right? So there's lots of little tricks the operating system can do with this stuff, and it's pretty clever and provides a lot of benefits. But yeah, we're going to start using this thing. Right, let's keep up with the chat and answer some questions. Oh, thank you so much for the sub there, Fabulous Flow. Yeah, Fabulous Flow. Thank you so much. Appreciate it. Right, so I hope these scribbles made a ton of sense. Let's keep up with chat. Are you going to make some arenas? Yeah, so we are going to probably have like a linear allocator, maybe an arena allocator, and have, allocate some memory arenas for this game. We're going to, at the core of it, we're going to be writing it with, like, this virtual memory is going to be the lowest level of the memory allocation. It's going to go in our OS abstraction. And on top of that, we will make these other allocators that we are going to primarily use. But again, we'll keep it simple. We'll probably just start with a linear allocator at first, and as we need more, we'll make the more complicated ones. That's cool. Yeah, I've always wanted to get into operating system stuff, Tempora. So just reading your comment, the short-lived attempt at operating system programming. Yeah, it's something I've always wanted to do, but never got around to doing it because I want to finish. Like, all there's more stuff I wanted to understand with game programming, Been enjoying the last few streams of your engine development. Have learned a lot from you. Thank you so much, Alex. Appreciate it. Yeah, if you have any questions, feel free to ask if they're on topic in the chat, or there is a Discord channel you can hop in and ask more off-topic questions there. Feel free. It happens every CPU RAM access, pretty much. Yeah. Unless it's in the kernel. The kernel gets around this. The kernel disables this and then gets sort of... I think it has got slightly quicker access. I'm not sure on the speed. The speed impact, to be honest. You can see what people do when also invited also. Oh no, it's a different thing. Yep. How does the MMU swap between what it stores and resident in memory? Does kernel code tell it what... Ooh. How does the MMU swap between what it stores resident in memory? The kernel code tell it like to get queried. Right. Yeah, so this MMU thing, if you look at like the OS dev wiki about the MMU, I think this is answering your question, Kappa. If it doesn't, please give me a different way of saying it. But essentially what happens is this MMU, these lookup tables for the MMU, you basically have that, the kernel stores those in memory. Like if you can cat these in the in Linux. You can say cat proc, and you get all your processes, right? And you can literally get the virtual memory. Where is it? The memory maps. That's it. Maybe not. I think you might have to have a. You might have to have certain permissions to see this, but essentially the kernel keeps track of all of the mappings of from virtual memory to physical memory for every single process. And then what happens is when your process gets CPU time and it does the context switching, part of that context switching is it's going to switch the virtual memory, the MMU is going to sort of load in the table, the lookup table stuff for your process, right? And it can do, there's an MMU API for x86, for instance. And if you look in the OS Dev Wiki stuff for it, you will see. Continue to write C code in the terminal text editor. How do you debug your code source level with? Yeah, so Probe N. What we use is so I use this front end to GDB called GF, right? And it's pretty good. Like, so I highly recommend it. So I run it through the terminal like regular GDB. So it's made by Naxt. I'll drop it in the chat. And yeah, so it's pretty awesome. You still have to know some GDB commands, but it gives you like a stack visualization. Like if I was to say break on GPU, I don't know, frame start, there we go, run it, right? Runs it, breaks in here. You can see the stack on the right hand side, which is pretty good. You've got access to the threads here as well, just clicking it. There's tons of stuff that I don't even use, but that are available. There's even like stuff you can pay for and get extra access. But some really cool parts is you can sort of like hold control and say run until this line here. But another thing you can do is you can hold shift and skip the instruction pointer to that line and really skip a section of code. So there's lots of like interesting little things here. But yeah, typically you have to sort of know how to dance around with GDB in the terminal. But yeah, you can also view your breakpoints here. But anyway, this is what I use. Out of context, can you recommend any textbook for computer graphics for beginners? I don't know. Yes, the problem is giving someone advice for getting into graphics programming is super difficult. Currently, it's like the most crazy subpart in programming. Like there's just so many weird stuff going on now. There's like Vulkan, Metal, DirectX 12. There are all these weird low-level things that people have to really understand and really complicated. And then there's a high-level part to render program, like graphics programming. And then if I was to tell you to learn OpenGL like I'm going to point you to, the problem is this doesn't map. It's such an old API that doesn't map to what the GPU does. So, learn OpenGL.com though has some decent sort of like things on to teach you how to sort of like, you know what, I'll link it. So with learnopenGL.com, it gives you some decent ways to sort of learn the high level things about like if you just do some 3D rendering. So it can teach you about like these things called transforms and thinking about like the maths behind it, and then go into like coordinate systems and translating between different spaces using matrices. And then you can go into stuff like lighting, materials, shadows basically, and some advanced stuff like all these things here, and it also has some even more advanced topics down here. So it really is a good resource to learn the high level things. But in terms of like how a modern GPU works, you're probably not going to understand it by going through this. It's another whole section, and it's really overcomplicated nowadays, unfortunately. But there's a new sort of thing which is coming called like web GPU. A lot of new people are jumping on it. So if you probably follow this community of web GPU, there's probably a whole bunch of new tutorials up and coming that I don't even know about. So I highly recommend, if you like, maybe look at the Learn OpenGL stuff, and maybe if you look into this web GPU thing, and sort of see the community around this, and maybe there's some stuff coming out. Because it's an abstraction that sits on top of Vulkan, Metal, and any other graphics API, and kind of it translates into those, and it's slightly higher level. Like if you're learning, it might be a good direction to go. I don't know though, because I'm not using it. I've just had a brief look at it. Oh, hey there, Downsy. How you doing? How's it going? How you been? Good to see you. How did I miss that? Oi, oi, oi. Yes, my goal is to finish a game. What is OS Dev Wiki? It's the place where people learn about making operating systems. So if you go to OS Dev Wiki MMU, Memory Management Unit, you can sort of see how operating systems set up this TLB or this virtual memory thing. And effectively, if you want to learn how to make operating systems, OS Dev Wiki has tons of wiki pages, right? So definitely check that out if you're interested. It's some rabbit hole I'd love to go into, but it's not, unfortunately, something I have time for yet. Maybe when I'm like 65 or whatever the age is now to retire. Right, I believe we're caught up. Excellent. So we've described virtual memory, and hopefully everyone understood these cave drawings. That is good. So okay, so now we'll talk about the pros and cons, and we're going to list them all out, right? So if we were to open up a new thing and just say, right, pros, let's zoom this thing in. Oh, maybe not. I should have done a new thing. I don't know my zoom level. That's the one I want. Okay, we'll close this one, open up a new one, because I want to independently zoom. Rightio. Not that button. Okay, pros. What are the pros of virtual memory? What are the cons of virtual memory? Why might you want to use it in an application? Okay. Hey there, VMT. Good to see you. Welcome back. Welcome back. But yeah, how's things been? How you been doing? So, the pros of virtual memory is that it is the lowest level, right? / gives you the most control, right? When it comes to allocating memory, right? So okay. So you can understand how it works at the lowest level and leverage that in your application to maybe get some enhancements in speed, or maybe simplify the code, right? So maybe you could say like, um, yeah, so this, right. So it is basically like works on most, okay, on all modern OSs that we care about. But a con about this is that it doesn't work on maybe some embedded systems that you might want to program on, right? Okay, I'm not really an embedded systems guy, but I'm sure this is true. Someone can correct me if that's not true. You know, and then also web assembly. It doesn't work in WebAssembly. Crazy thing. The WebAssembly guys didn't design it in mind with virtual memory for some reason. This is one of the reasons why I wouldn't be compiling my C code to WebAssembly, because they don't expose something which works on it works on phones, it works on Linux, BSD, Windows, Mac, Android, iOS. It works on all the stuff you want to care about, even things we can't speak about too much in public. But it works on basically everything you want to program for, right? So cons are it doesn't work on some embedded systems potentially, and WebAssembly, right? But we don't want to target these things, so it's okay. Yeah. Yeah, I don't know why they didn't do it. It's so silly. They're like, well, maybe it doesn't have it in the future. It's a bit like saying, like, I don't know. We might have pointers in the future, so we don't do pointers. It's okay. I don't know. It's just like stupid weird. Hey there, Unreality. Looking nice. Awesome. Sweet. What sort of project you working on? Are you doing some making a game using Vulkan? Um, Virtual memory is the thing that all CPUs with an MMU and modern terms, all application processors, and excludes all microcontrollers. Okay, good. Right. Yeah, because I guess like there's some ARM CPUs that you have that are embedded, right? That might support it. Yeah. WebAssembly is kind of cool, but they're like 80% of the way there, you know, in a way with it. And there's like some anyway. Um, so there's some like neat tricks you can do, right? Neat tricks you can do. So you can sort of like, so one of the neat tricks is you can sort of reserve a whole address range and have stable point. Like, so something I didn't really explain, but I'm gonna draw it out now. Is right. So you have your virtual address space. Maybe you like reserve. You can reserve, right? You can reserve an address range in your virtual memory space, and then so you have your physical memory up here, right? Imagine these are 4K pages, right? And then this But if we were to grow our array, imagine if we have a pointer into this array. And imagine now we want to grow our array. With virtual memory, what you can just do is you can just say, okay, we'll commit this page. And maybe we'll commit this page as well, because our growing strategy is to be a bit more generous on the number of pages we extend by. And we can map those pages in, allocate some more memory. And now this pointer didn't have to be patched. The pointer is not going to be pointing to a wrong memory location because we've resized our array. The array stayed in the same place in virtual memory, and we simply just extended the allocation and took more memory from the operating system. So this is another benefit, one of the neat tricks you can do. This is a neat trick to do with, like, you know, to help with stable pointers. And you can, there's also another neat trick. There's also another neat trick you can do, which is basically a ring buffer. So I did say I didn't want to talk about the advanced tricks, but it is part of the pros. So maybe we'll go and talk about this thing. So because your virtual wait, did the music stop? Let's keep that going. Oh, what happened to the stream? No. Are we back? Alright, sorry about that. I don't know if that was my end or not. I don't know how I can check. Well, it seems stable since whenever, I don't know whenever that is. But yeah, apologies for that. Right. Good. With ARM Cortex A, full-blown application processor family and multi-controller families. Okay. Interesting. Good to know. Yeah, microcontrollers, virtual memory and TLB are expensive because they require a bit of converters for every bit of the virtual memory. Right. Okay. Good. Right. So there's neat tricks where it helps with stable pointers where we can just grow arrays if we just reserve a virtual address space and then commit the pages later on. So there's another neat trick you can do with like a ring buffer, which is pretty, it's pretty, the code to get this thing to go is very weird, but as soon as you have it in your code base, so you can have like a page, you can have pages in virtual address space, right? So imagine you got 2 pages in virtual address space, and this represents a ring buffer, right? A ring buffer meaning, ideally, whenever you read off the end here, you want to go all the way back to the beginning again, here, right? So since the virtual memory pages just map to physical pages, right? They just essentially point to ranges in physical memory. Like it's possible to have pages point to the same physical address space. Now the API to do this in operating systems is the most crazy API you'll probably ever see, and it's a lot more complicated to do this, but you can get this thing to go, which means if you were to read you know, read off the end of this one and just read into this page, this is the same as reading into there, right? Because they point to the same physical memory. So you can essentially like have a cursor that sort of just gradually increments, right? And then you might write into it over here or something like that. But then you've got to make sure you sort of like mod the cursor back into the range, to start back here. So it saves you having to do to split your, if you've ever done like an API for a queue, you will know that you would have to sort of like potentially break your copy into two pieces, because it might go off the end of the contiguous block in memory. But with this magic ring buffer trick, you can essentially wipe that problem away and just rely on the fact that virtual memory will wrap it around for you. So it's pretty cool design. So these are some neat tricks you can get with it. We can also assume that memory is zeroed. Right? Zeroed memory, and we can rely on that to make sure, so we don't have to mem set it. Thank you, appreciate that. Appreciate the tip there. Yeah, so I think these are right. So what are the cons of virtual memory? It doesn't work across all the modern operating systems. And you have to build your own allocators on top. Build your own custom allocators on top. So it requires you to sort of understand this and have a bit of knowledge, but when you do, again, you have the control, right? Which means you can, I guess that's also a benefit, is we can now build our own custom allocators on top of this and build them specifically for our application, and the way we're going to allocate memory. I think this is basically the pros and cons. What other cons does it have? It's probably yeah, using Manjaro Linux. Highly recommend it because it's a pretty decent Arch setup out of the box. Okay, so with this in mind, should we get doing our abstraction for this? So let's talk about how do we what are the main APIs on Linux and Windows that we use, and how do they differ, maybe? Or should we talk about the abstraction first? I don't know. Right, man, mmap. So if you look for mmap, this effectively on all of the Unix-based operating systems, Linux, Mac, Windows, FreeBSD I meant, sorry. Linux, Mac, FreeBSD, you got this mmap thing. So you can pass in either null into the address, or you can request a virtual memory address that you want to map. So you could say, hey, I want to map this specific place in memory for some reason. But typically you don't really care about this, but you can if you want. And you specify a length or the size of the allocation we're going to make. And remember, it has to be rounded up to the nearest page size, which is 4K. And you can have these different protections. Now this protection thing is interesting. With the protections, you see, you can say it's read-only. You can make it as writable, or can this memory be executed? And there's also some other things you can do with it as well, but these are the main ones. And when you map this memory, you don't have to do, you can change the protection later on via mprotect. But yeah, you can see that later on. There's also some flags. So the flags basically dictate like, can I share this across processes? Or is it private to my process? Oh, there's a whole bunch of them. What are they? What's that anonymous one again? I'm not sure if I can see the flags here, but yeah, there's some flags we need to look into. Right, and you can also, oh my days, I completely forgot. You can also map files with mmap. So with mmap, you can map a file from disk into the virtual address space, and the operating system will read it in just in time when you access the memory. So you can also map files using this API. And then it gives you back a pointer to the virtual memory that you've just allocated. So remember, this is a system call, so it will probably take some time to complete. So you probably want to call this once, allocate a nice slab of memory, and you can subdivide that between your different allocators, right? But yeah, that's more of a performance thing. Then on Windows, you have virtual alloc. So virtual alloc kind of works like mmap, but it doesn't allow you to map files. There's a different API for that. So there is a difference between virtual alloc, well, Linux, and the way Windows works. Actually, we've got to explain that. Pros and cons of garbage collectors, no way. The length does not have to be page aligned. If you map a file, the offset has to be page aligned. Oh. Right, so if you map a file, okay, interesting. That's released on Linux 6, just got a bit in the rear because of it. Oh, right, nice. Yeah, anonymous means not file backed. I think that's right. Sounds familiar. Cool, what's the dual boot my Linux laptop between Debian Mint and Manjaro? Nice. Am I doing C for my job? Yeah, we're doing C for the job. Well, C++ really. At work. Yeah, potentially would be more sense to the abstraction first, maybe. Yeah, so let's talk about the main difference between Linux and Windows, the way it works. So with Windows, you got this virtual alloc, and you do pass in the protection, right? You got that you can request an address, but it doesn't matter. It gives you back a pointer. This is what LP void is. It's a pointer to void. And then the size again. So with Windows, they do have a page size of 4K typically. They can have a larger page size, I think. But they have a different thing called page granularity. Now, what page granularity means is when you make your virtual alloc, your size has to be rounded up to the page granularity. Now, that size is actually 64K. So you have to, in terms of the, so I think on Windows, I'm not exactly sure on this, but when you have your virtual memory that you request, right? This has to be like when you reserve the virtual memory space, this is done in regions of 64K on Windows, but you can manually commit for, what was I in 4 gig? 4K. You can manually commit 4K to a physical place in RAM, right? So yeah. So from what I understand, that is how it works. I wouldn't take it for verbatim though, but there's also another limitation on Windows. Virtual free, which sends this back, gives this back to the operating system, is actually very limited on Windows. On Windows, if you virtual alloc 64K, because that's the least you can do, you can only free that whole virtual alloc. So, sorry, what's the way of saying this? You can decommit individual pages with the decommit flag. So there's decommit, where is it? Decommit here. Mem decommit in the free type, right? You can decommit individual pages, that's fine. But what you can't do is you can't release. So you have to release this whole virtual memory reservation at once. So say if I reserved even more in one virtual alloc and I reserved that address space, you have to, when you call virtual memory free and release, free with the release type, it will release the whole thing. Whereas if you're doing it on more of like like you have unmap. Where's unmap on the Unixes? Unmap. No, it's you. Which one is it? It is unmap, isn't it? Anyway, I can't see a man page. Maybe it's on the second page of the man page. Oh, M unmap. Such a scrub. I don't even remember this. So yeah, this is the thing you use to unmap your virtual memory. So you take your reserved address space and you give it, like, you unreserve that now, right? And you obviously decommit any pages back to the operating system. So if you're doing this on like a Unix operating system, you can technically take an individual 4K and you can just decommit. Sorry, you can make this region like not reserved anymore. But yeah, that's not cross-platform, unfortunately. So we're going to take this into account on our design, and it's going to work the way the Windows. We're going to emulate it to work the way Windows does, because we're going to run on Windows. Okay, what sort of question do you have? I'm just terrible. What's the question about your memory? I just thought with C++ seems too scary. You got this. Don't worry about it. Scary is good. There's actually a more readable version on FreeBSD. Okay. Nico. Right. So now let's talk about the virtual memory abstraction. So I've already written one of these before, so we're just going to bring it in. So remember, if we go into our operating system folder in the GameOut engine, what you'll find is there is a OS interface, and we're going to implement that. All right. Source os.h. So we haven't really ordered this in any way. Should probably let's take one of my headers. So maybe we'll have an event section. Operating system events. There's the DLL loading, because we've got DLL loading already, because we're loading Vulkan via DLL. We also want to have the We also want to have the virtual memory stuff, right? Okay, so let's go and get that from, so I made one earlier, put it here. Where is it? All right, this is the thing, fully documented, and we're gonna go and explain it. And yeah, we'll here it is. So we're gonna give it a bit of a refactor, obviously, but this is the idea. So let's replace with core. Then we're going to replace with the core. Oh no, this is operating system, isn't it? Don't mind me. I just want to create a mobile app for information sharing. I just want to use virtual memory to store future updates and also store a vast amount of information. I distribute in an ad support app. Makes any sense though. I'm not sure what you mean by you want to use virtual memory to store future updates. I don't like, you know, I think you're like referring to some high level concepts, but I don't know how the low level, oh, I just did the wrong thing again. I don't know how the low level like thing, virtual memory, actually helps you achieve that. You know, it's sort of like those things seem to sit on top of a couple of layers to, you know what I mean? Right, nearly there. And then we can explain what this does. All right. Here we go. So, right, I've got to fix this. You pointer. And we need an operating system result in some way, which is kind of cool because we haven't had one of these yet, but we kind of want to have like an enum. Probably so what I want to say is, like, you know, there's probably the error messages. Are we gonna have different types of success or just error codes? I know, I think there's only one success. So yeah, we'll do and then we'll have more. So anything that's not 0 will be an error, right? So we'll say like, yeah, we'll see what they map to. But anyway, we've got this result now. So what, you know, maybe it's like the file doesn't exist or directory doesn't exist, those sorts of errors. Okay. So there's two different types of page size, right? There's a size of an actual page that you can individually commit and decommit, right? Commit and decommit just mean give me a physical page for this virtual address range, and decommit means, hey, operating system, take that physical memory back and use it for other things. And then there's this thing called alloc alignment, right? Which is that page, which on Windows is that page granularity thing, that we just talked about, how on Windows it's 64K. So we've broken up into these two concepts, and you can, like, when we boot up the application, we query these and we store them in global variables, and then these two functions are a way of retrieving those, and that's it, right? Right. So, man, this is not the one I wanted. This is not the abstraction I wanted. Why didn't I look at it? Alloc, dealloc. Nah, this is not the abstraction I wanted. Or is it? Let's have a think. Allocates ranges of virtual address space. When a page in this allocated address space is initially accessed, the OS will assign a physical page memory to it that will contain. Yeah, this is not good. This is not good. Right. So I have a reserve. Yep. We'll have a reserve. We'll have a commit, decommit, and we'll also have a probably, you know, I'm not really a fan of the word free. Release. There we go. Okay. So I'll probably just redo these. Right. So you release the address size. Nice. Commit address size, and then decommit address size. Is there any protection? Yeah, we also maybe want to wait. I don't know if we want to wait to change the protection. Maybe we do. Yeah, we might want to. Yeah, protection set. Excellent. Yeah. Right, so let's just get some documentation sorted out for these. So allocate a range of virtual address space. But do not but we don't commit anything. Yeah, because you can reserve and you can commit pages in one go. Yeah, you see on Windows you can reserve and commit. Yeah, maybe we want a way to reserve and commit as well as an optional flag in some way, because then it's one call to the operating system, not two calls. But we want to make them work the same way. So we might have another one called reserve and commit. Because then it's one call, I guess. Right, so allocate a range of virtual memory address space, but do not commit any physical pages to it. And we'll just say, you know, a call to, oh, wrong one. Damn it. A call to OS virtual memory commit must be called on a subrange, you know, on the pages a future call to on the reserved on a range of the reserved address space before use or something like that. A future call to commit must be called on a range of the reserved address space before use. Something like that. On Windows, you cannot deallocate individual pages of this address space. You can only decommit full. So, yeah, we must put a warning. Yeah, we'll leave that warning in there. You cannot deallocate individual pages of this address space. You can only deallocate the full allocated address range has been issued by this function call. There are no restrictions on protection. Oh, there are restrictions on protection? You can change protection to number of pages, but they all must come from the same call they were allocated with. Oh, I forgot that one. So if you reserve two separate regions of address space, you can't mem protect over both virtual memory reserves. Basically, it's a bit silly. Yeah. Ugh, forgot about that one. Thank you, past comments. The requested, you know, do we ever want this in our application? Right? Do I ever want this? Because this is a custom. You know, this is an API for what we want, and I cannot think of I ever want this. Right? So let's just not have that. Right? Let's make the API a lot more simple. Let's just say, you know, size. Right? I cannot think of us saying, you know, at this specific address range do this. It's just not good, because that works differently across operating systems as well. On Windows, it maybe rounds up if you don't get that one, or on Linux it rounds down or something. Yeah. The size in bytes you wish to reserve. In the virtual memory address space. So you spell contiguous. Yeah, it is good. Right. Allocate a contiguous range of virtual address space, but not many physical pages to it. Yep. Oh no. Right, okay, let's just leave it on. Protection, that is right, okay. Size in bytes you wish to reserve in the virtual memory address space must be aligned to the return value of not size. Where is it? It's alloc align. So we'll probably call this the reserve align. Yeah. Okay. The alignment of the address of a virtual memory allocation. This is used as the alignment of Wait a minute, it's page granularity now, isn't it? No, actually we don't need that anymore. Since we don't have the reserve address, we don't need that reserve alignment, because you can commit pages less than the, yeah, that's fine. So it is actually page size. I got that wrong. What is the memory allowed to be used for, right? And then the out pointer is a pointer to a value that is set to the start of the virtual, right? Yep. Awesome. Right, so that's our reserve function. Then we've got this second one, which is reserve and commit. Right, so we want to say like allocate a contiguous range of virtual and commits. So commits any physical pages to it. And right, so that by the time you access any of the memory, it will contain zeros, or zeroed. It will but by the time you access that memory, it will contain zeroed. Well, what's the good way of saying it? So by the time you access that memory, it will be ready to use and contain zeroed data. Something like that. Hey there, Sully. How you been? How's it going? Then the same comment before. Yeah, it's a bit hot, Sully. I'm not sure we'll quite do a hot tub stream though, you know. But yeah. Getting quite dark. Maybe we'll switch on a light in a minute. So yeah, we just copied and pasted that. That's pretty good, isn't it? Right, we removed that requested address since we're not going to use it for this game at all, so we're not going to do that. Release. So release gives the committed pages back to the OS and releases the address space zero initialized, eh? Interesting. Maybe that's a better way of saying it. Yeah, he's AMD. I have an NVIDIA for work. Yeah. We'll be ready to use and be zero initialized, I guess. Maybe there's a nice way of saying it. Okay, so commit, or release, sorry, gives the commit pages back to the operating system and releases the address space Okay. Releases the address space the contiguous range of virtual address space, and decommits any physical pages back to the operating system. Whatever. So on Unix-based, so we want to say like warning on Unix-based systems, isn't it? You can target invisible, yeah. So you want to say like warning. So, because there's no way to like ensure this happens if you're running on another operating system, which kind of sucks from what I know. On Unix-based systems only, you can target individual pages in the allocation. Right. On Windows, you can deallocate individual pages of the address space. You can only deallocate the full allocation that was allocated by reserve. Also, the size is ignored on Windows. Yes. On Unix-based systems only, you can target individual pages of the allocation, and it will allow use target individual pages of the allocation, and we want to avoid this. To avoid this, as it will not be compatible with Windows. There we go. So you give the start of the pages you wish to deallocate. So we're going to say this as the start of the pointer. Maybe we call it reserved. The pointer to the start of the virtual address space reserved with this. That you wish to release. The size in bytes of the memory you wish to release, that was passed into reserve when must be aligned to the page size. I'm not going to say any of that because it's just the same number. It's the same restrictions, obviously, from there, right? 0 on success. 0 on success, more like returns 6. Do you do remap? Oh, sorry, do you remap in Vulkan? Yes. So I've got my own custom key bindings, basically. Some of them are very similar to traditional Vim, but I've remapped quite a lot of it to where it makes a lot more sense to what I want to do. But yeah, I basically relearned Vim and how to type. So take it because of virtual memory software became La La Land. Not sure if we can be thanking it or skinning it alive. What do you mean? It became La La Land. Yeah, better security, restriction of resources across multiple processes, making life easier, reasoning. Yes, the thing is about so the thing is about virtual memory is that it's a thing that like no one leverages when they write a program nowadays. And if people did leverage it, they can do some really awesome things. Like they can assume the memory zeroed. They can uh, keep stable point. They can grow arrays without doing. They can grow an array. Like imagine if you have an array, right? I've made an array. Maybe this is a stud vector, as people like to do when they're doing their CPPs all over the wall and everything. You know, you might have this stud vector that you've like allocated and you sort of like write to the memory, and then you know, you push another element on and it's like, oh, this is full, right? Well, now the way it works is it resizes and it allocates another bit of, this is a very simple take of how it works. It basically times the capacity by 2, copies this memory into here, right? And then finally, after doing the allocation and the copy, you can then push that next element on, right? But oh yeah, and then you can free this back, right? Free it back to the, whatever the operating system allocator is. But what happens if I had a pointer pointing into here, right? Well, now that pointer's pointing to some freed memory, and it's not pointing into the correct place in here. So with virtual memory, you can basically just like commit more memory as you go. There's lots of good tricks you can do. And that's how we've structured the HCC compiler actually, is we use virtual memory. So we have these massive arrays, and we just allocate more as we need it. So yeah, there's tons of interesting tricks you can do. Because it's slow. Hey, Nadila, what's the slow bit you're referring to? On the changer now we had to when I split control Comac, relearning Vim time. Although virtual memory retrofit is a small block allocator using virtual memory ranges to encode the size information. Is a small block allocator using the address ranges to encode the size information. Right, yeah, I think that's just Yeah, so what you're saying is store the size in the block. But yeah, then I've got to assume that, yeah, so I can store the size in the virtual memory that I allocate, right? Yeah, but then I don't get to use the whole 4K or, the whole allocation, I guess. Bit of a problem. Because you can assume it's aligned as well to any data type that way. But maybe you can store it at the end of the allocation? So that's, I don't know. Virtual memory feels like something could be implemented faster if it was a specified case. Hmm. I'm not sure. Yeah, it does. Yeah, I guess is a very general solution, but that is they have custom hardware to make it faster, right? On main platform, I decided to detect memory corruption by making each allocation virtual memory allocation and protect before or after it. It was uber slow, FPS tanked. Oh, yeah. Yeah, allocating directly with virtual memory is not good, right? But maybe you reduce the amount you call in using virtual memory, right? You reserve the things. But yeah, you want to limit that, isn't it? But yeah. Um, right. Okay, that's good. Now on commit. Allocate. Ooh. Um, so commit physical pages to a virtual address space, I guess. To a range. To a contiguous range of virtual address space so that for the next time you access the memory, it will be ready to use and be zero initialized. So this one, there's no warning. We need a parameter to say the address is the address. The address must be aligned to the return value of this, right? Okay, must have been within the range, the address range reserved with OS vert mem reserve, right? And must be aligned to that. Size in bytes wish to reserve. Yep. Or maybe we'll put the comment here and just say like the range of virtual must be reserved using this first. Okay, so then I can just say drop that, join that line. Cool. Yep, protection. Do we need protection? Nope. And result. Cool. Decommit is just saying returning that back to the OS. Right, so decommits any physical pages back to the OS, right? But the range of virtual address space will remain reserved. The memory yeah, something like that. You wish to reserve. Ooh. decommit pages for cool. Gives the allocated pages back. Right, what is this? Okay, no. That one gets deleted. Yes. Nearly there now, and then we can start implementing all this. Oh. All right. So this is an interesting question I did have for you. So are you talking about constantly allocating with virtual memory, or are you talking about you've made all of your allocations and done no more, and it's still ground to a halt? Like, which one is it? Because yeah, I think if you're doing lots of calls to virtual memory, it's not going to be good because it requires system calls and setup behind the scenes. Constantly making allocations, yeah. Yeah, virtual memory is not the fastest way to allocate memory, unfortunately, and it will slow stuff down. I think you got to be perhaps maybe you can reserve a big chunk of it and then just call memprotect afterwards. Right. Yeah, I think what's interesting is on some operating systems as well as you can batch the system calls, right? Um, but yeah, on most modern OSs you cannot do that. Um, but yeah. Change the protection of a range of memory. This memory must be allocated with. That function is wrong. With reserve. So if you reserve, we've not committed. Virtual address space. This memory must have been reserved with this thing. On Windows, you cannot change the protection of a number of pages, but they must come from the same call. So yeah, you cannot change the protection. You can change the protection of any number of pages within a reservation, but they cannot come. But they must all come from the same call. They were reserved with. Reserved with. So like on Unix platforms, this will go. This will go. This will work. So be aware as we want it to work on Windows as well. Right. Change the protection format to round to the nearest of those. Thank you. Thank you. Protection, bam. Oh, did I say host? Oh, that's for you in it. Don't worry. Reset. So this is an interesting one. Maybe you want to reset the physical pages. Give the physical pages back to the OS, but we'll keep the address space allocated. Interesting. Yeah, gives the physical pages back to the OS, but we'll keep the address space committed. Right, this is weird to kind of say, but you're sort of saying to the OS, I won't need these pages, but next time I access them, I want them to be zero. Like, give me fresh pages. This will give you zeroed memory when the target pages in the address space are next accessed. Right. So this is like, right. This is the same as decommitting and committing decommitting the address space, right? The range of address space. Right, start of the page you wish to reset, must be aligned to blah. Yeah, cool, that's a good one. Then this one is like force. I don't know if I want to do this one. I've heard there's some performance. I've heard that there's a way to, if you preload the pages you're going to be writing to. Yeah, you know, I think we'll implement this one. We'll do it. After virtual reserve or reset, the target address space will not yet have any physical pages assigned to the virtual pages. These will get assigned when they are first accessed. See, what we're saying is really commit. Reserve and commit. This function accesses all the specified pages. So the operating system assigns physical pages all at once. This will prevent the system from switching back to the kernel when you first access the pages. Yeah, I'm not sure how correct this is. So we need to test this in the future. But so the idea is we're just going to for loop over all the pages, do a read, right? Just do a read. And we've got to make sure the compiler doesn't optimize this out. So we do a read, and that will force the OS to load the page in for us for that virtual address. Yeah, it'll do a physical page map. So I've heard from someone, so I want to test this out, that if you're going to be accessing a whole range of pages in a short period of time, it's best to get those things committed to some physical address rather than accessing a page, doing a ton of work, and then maybe accessing the next page, doing a ton of work, accessing the next page. I've heard it's best to have them already pre-committed. So yeah, I want to see if that's all correct, right? So anyway, these are the functions we're going to implement. Let's do it. Yeah. Hmm. Well, yeah, I don't know about that. I think it's decent if you know the lifetime. Yeah. Well, the hope is, Nodilo. I think what we want to do with this game is just reserve everything that we need up front. Well, we'll try and do that as much as possible, and like, yeah, maybe we'll write our own little system so we sort of have control over how the whole system works rather than relying on how a particular heap allocation heap allocator works, right? So that's the idea with this thing. Um, right. So I want to put this probably about here. So let's implement this on the Linuxes. Let's put this over the DL open stuff. Right. So we have a right, let's get rid of all these comments because this is the implementations. There's no point in having the comments repeated, right? So okay. So, virtual alloc. Is the protect always set? The pages are being committed, you specify any one of the member protect. Are being committed, you can specify one of the member states. Right. So reserve shouldn't take in a protection. The protection needs to be specified when you commit. So that one out. So we're saying commit. Excellent. Right. So in the OS Linux internal, we want to keep hold of this page size here. So we're just going to be returning OS Linux, GOS Linux, right? Page size. So when we boot up the OS subsystem, we just want to make sure we initialize that thing up, right? So we're going to say GOS Linux. So there's a function to call, and I keep forgetting this, but there's a good one to call. So on Linux, there's get page size, I think. Linux. But there's also another one where you get it from the config. There's get page size, and there's also, yeah, pull application should employ this instead of get page size. Right, this one. Okay. There you go. Sysconf. Man sysconf. The returns are long. Right. So we'll get the page size that way. And it'll just be 4K, so just keep returning that there. The reason why we cache into a global is because I've had those functions like spontaneously fail on me, so it's just better if you do it this way. All right, so next one is reserve. So in order to reserve, you want to use mmap. Then so you get back a pointer to it. So you say address. So we'll pass in null to say we don't care what the address is that you give us, just give us back an address. Pass in the size. Now we could assert here and say must be a multiple, right? So I think we can do our core debug assertions, and we're going to say size of page size. Size and GOS Linux dot page size, right? What else? So we need where's mmap? Right, so we want to have a protection. So we want to translate the protection over. So we need a nice internal function where we can just get the virtual memory protection. So that returns an int, and we give it our super nice virtual memory protection. My point was that I think that virtual memory abstraction is just too low level. If you have a specific allocation strategy in mind, would you implement it behind an... I'd implement it behind an allocator interface instead. Nice. By the way, what are you attempting to do? What special allocation design do you want to use? So you'd implement it behind an interface instead. Right. Yeah, so what I plan on doing is just like this is my OS layer, right? So I could just call it like OS allocate, right? But then it will use virtual memory under the hood, right, to allocate memory, because I don't want to go through through malloc, right? It would just be good to get access to what malloc is doing behind the scenes. But yeah, on top of that plan, I am building custom allocators though on top of that. But they're going to be fed memory that comes from virtual memory. Now, if I want to do any specific special stuff to do with having maybe a massive array that we can commit more pages for later, maybe we'll do that as well. But again, I have to be careful and juggle like if we want you want to commit more than maybe a page at a time. But yeah. Yeah, it's just to have access to this stuff because it's quite powerful. But yeah, that's about it. Because it would just be good to have control over it as well. Right, so so we're just going to switch on this. So we're going to say switch on the protection, and then we'll say 5 at S. And so no access is probably just going to return 0. Google's getting worse. I'm trying to find the movies, and that's been part of, and it's not getting relevant results. Yeah. Yeah, I think Google is really getting worse, and so is YouTube as well when you try and search for something. Like, I used to always find what I needed. I don't know if it's because I'm searching for more specific stuff now, or more advanced stuff now. But yeah, I just find it's very difficult to get the results I want a lot of the time. Is it because the internet's now filled with noise? Or is it because they're trying to feed you a very curated set of results now, and things are just really complicated? Whereas before it was maybe, I don't know. Execute with read. Execute, read, write. And I think they're all ORed, right? Cool. So if not, we just return 0. Hey, Under Closure, how you doing? Thank you for the sub, appreciate it. Yeah, doing good, man, doing good. Just been going over this whole virtual memory thing and describing it from the beginning, you know? Oh, we don't need the protection. So we can pass in 0 for protection. Just say prot equals 0 prot. But yeah, how's things been going with you? Then you want flags to be 0. Right, flags, well maybe not flag 0. FD and offset off T. FD offset. Where's the flags? We're going to slow those flags. Now I think we also need to include a bunch of things. Sysman, mman. Right, so you get back this, and it does return. So the flags, we've got to put in like we'll look at those flags. So we want private to say. Oh, mapping the same region in cases where. Okay, not that one. Create a copy and write mapping updates to the that's really not visible to other processes. Yep. So we want that one. And we probably want anonymous as well to say it's not a file. Anonymous. This mapping is not backed by any file. Its contents is initialized to 0. FD argument is ignored. Yep. So we're saying it's not a file. We're not mapping a file. Then we want to say if address is equal to that. It's called like no. There's an actual error. Map failed. So -1. Right? If it's equal to all bits on, we want to get the last operating system error. But that's just error number, isn't it? Right? But yeah, get last error, OS result. And then, this is void. So we'll implement that as well. Bear in mind, we're not going to actually fully complete it at all. We'll just complete it as and when we find out stuff, and obviously put to do in there to say, so, you know, to do complete. Switch, so you int the error no, error number, error no, and then you want to say switch error num. You know, maybe we don't need to hold the error. No, maybe we just do that. Case, and then we can handle those. So by default, case 0 is return success. Now we at default, we say unhandled core abort, unhandled OS error translation or OS error U, and then probably 0x x to have a hex representation of that as well. And there we go. So where do we get error no from? Error no.h, obviously. So this would be the thing we return whenever there's a problem. So there's a problem, and voila. And now we can return OS result success, set the ADDR out to ADDR, and voila. So there's the reserve. Yeah, you think you should want to push more clickability videos first and those results as well. Oh, clickbaity, sorry, videos. Yeah, the ones that get a lot of views basically. But yeah, like it used to be really good on YouTube where you used to be able to daisy chain through videos and find such good related content, but now it's just trash. I don't know. The YouTube search results used to be way better. It's not just about showing clickbaity videos. You used to be able to search for what you wanted and you used to be able to scroll through and find it. Now you can't search for anything. If you search for something, it's like, hey, I know what, instead of saying like, you know, say if I search for like some specific talk at GDC, right? Try and search for a specific talk at GDC. And maybe, or maybe not a specific one, you want to search for a type of talk at GDC, right? You will find one or two, and then it will show you a ton of crap that's not related. And maybe it'll start showing you more afterwards, but typically it just starts showing you GDC, like videos for GDC. And you're like, I didn't want this. I wanted specifically ones for rendering. And it just doesn't show you anymore. Because they want you to stop going through these rabbit holes that people get trapped through, I think. But no. Always going for a bunch of college reports. Cool. Cool. Hey there, Bonamatana. Maybe. Oh, they're required to be -1, is it? Okay, we'll do that. Thank you. Thanks for the catch there, guys. Right, -1. Appreciate it. Right, so reserve and commit on Linux at least. So, should we do the Windows one side by side? We'll do that side by side. Let's do it. So we'll get these two in, and we'll show the difference. So, for Linux, protection must You can do a commit no access. I don't know why you would though. Protection would be OS Linux. Flags, private, anonymous. See, so on this operating system, right, you like, because we set it to no access, it's gonna like crash when you access it, right, and give you like a seg fault in a way, or an access, or some signal where you failed to access it, right? But when we say commit, we're setting the protection to be. Wait, should we set it to a constant, like no access? Is there a constant for that? But it's basically 0. Yeah, none. That's it. Let's make it more explicit. Okay. So, yeah. So this will reserve and commit the page. Like, you know, as soon as you start reading the page after this function, it's gonna commit pages as soon as you read it. There'll be like a, yeah. It's kind of done automatically on the Unix platforms, whereas on Windows it's kind of explicit in a way. Well, kinda. On Windows, when you do your commit, you need to have enough RAM in your system. Yeah, you can't commit more pages than you have RAM in your system. That's the limitation. FT0 is standard in, no? Yeah, I think it is, yeah. Yeah. Hey there, Paula. Pilly Pally? Welcome. How you doing? Can it run Doom? No. Why not protect the page in mmap? Well, we have two versions, right? Reserve and commit, because this has got to run on both Linux and Windows, and they work slightly differently on Linux and Windows. Let's go into the Windows side of things and get this implemented on the Windowses. We'll copy this and bring it over. Rightio. So let's do the Windows one side by side. So, we're going to put it somewhere around, oh no, here. But I want to get that DLL thing. I really got to do some cleanup in this. We'll be doing that at some point. There we go. Right. So on the Windows, I also need a Windows internal. We're just going to be dropping that page size in there as well. I want to create something like what we had in GPU. We've got like a two layers of abstraction with this OS thing, because there's a lot of shared logic that we will be repeating with this, and it's not the best. So yeah, I want to get these two sorts of things. Windows, protection. Is it like a D word? It is something like that. D word, that's right. So we need these things in here as well. They're going to go just below here. So Where's the protection at? Protection constants. Let's get these guys. Right, page no access. I just realized we need to do that prot. None. That's it there. Okay, good. So page read only. Page read write. We want a page execute read. Execute read write. See, there's no write only, so that's the reason why we've done it this way, this enum, so we don't get that confusion. Okay, so we've got that now, which is good. Get the last Windows error. This is done with, I think it's called get last error. dword error, get last error, I think it is. Yeah, that one. So we can just call that error, error, error. Okay. So obviously we'll fill that as and when we can, as we find out stuff. So when we reserve OS G OS Windows, change all that. Then we want to set up. So I forgot the exact way to do it. We've got to get the system Win32 get page size. There's a system info or something like that. I don't know where you do it. Get system info, this is it. So you define a system info. Yep. Sys info. Then you, this function with the address of sysinfo. Then you can say Windows page size equals sysinfo DW page size, something like that. Now there is the other one obviously, but we don't need that because we've changed our abstractions, so it's a lot more simple than it was before. DW page size, that's it. So we get back that D word for there, bam. So now in reserve, right. So we did that check to make sure it's a multiple, that's good. You know, we should probably also check to make sure it's not null. Because if not, you get a really bad error from the operating system. Must not be null. Right. Let's make that better. Okay. So with Windows, you're going to use virtual alloc, right? So let's get that one sorted out. So this is reserve. So we want to call this, we get back our address. Now the address can be null. Yeah, if it's null, it's a problem. So if address equals null, then Windows get last error. We'll return that. Then the requested address is null because we don't want to request a specific address. The size is passed in there. We want to do a allocation type. So this is going to be reserve. Like that. And the protection doesn't matter. Right, so we say D word protection equals probably just that page no access, right? D prop. So that will then return us, like that's everything we need. And there you go. So to do the same, so you need to do a similar sort of thing here. Protection equals OS Windows protection. And we're passing our protection enum to translate that to the Windows one. Then we want to call mem and commit, right? Do you have a Windows machine to test this all out? Yeah, so we will, like, I dual boot Windows on this machine, and basically when I get it up and running on this operating system here, right, if there's a lot of work to do, I'll try and get it up and running in a whole stream, but because we're kind of implementing it here, I might just fix it up off stream and then just commit it, right? Because it's just gonna have probably have a few compile errors, but the logic is probably gonna be fine. But yeah, if the logic isn't fine, I'll obviously, like, on the next stream kind of mention what the problem was if that's changed anything. But yeah, that's the idea in general. Like, if it's a more complicated thing like implementing keyboard input, I'll probably do that on Windows itself because it needs some actual feedback to get that thing working, you know. But yeah, so we need to use mem commit as well and use all those things together, like so. Now release. So we'll hop over to the OS Linux side of things. And for OS Linux, you want to use munmap. So you pass in the reserved address and the size. And with munmap, you do get an int back. So you do get invalid values, but shall return 0. Right. So it's not equal to 0. Then we're going to return the get lost error. And that's the release function done. Although we do want to have this, right? And we do kind of want to have the same for the address. Something like that, right? It's not line to multiple page size. It'd be nice to write Windows friendly C++ on Linux. Well, that's the sort of idea with this abstraction, right? Is like, or when we write this OS abstraction, is that providing you follow the rules, the code should just run on Windows no problem, right? It's the whole point of the abstraction layer. But yeah, it would be nice to be able to write Windows code and test it on Linux. That is good, right? Like, as an example, we did we did write basically the whole, when we had the GPU abstraction written up, well, sorry, when we had the initial OS parts to it written up, we pretty much just all did it on, we did it on a different operating system, and when I tested it on Windows, it just worked, right, a lot of the time. So it was not too bad. Have you heard of mshare, the special system called to suggested by the Oracle DB team? Good for sharing memory pages. Ooh. I've not heard about that one. Should we take a look? Is that not on Linux? I don't think that's a real thing, right? Sharing page tables mshare allows you to share page. Oh, really? Huh. Right. Yeah, there's some little, there's like madvise, which we're going to be using in a minute. Madvise. There's mremap as well. That's an interesting one. We're not going to be using that. And mlock, yeah, that's another one. But I didn't know about mshare. Alright, I'll take a look into that off stream. I'll see. But yeah, thank you for that. So how do we do the release on the Windowses? So for that, you need to use virtual free. Virtual free, put in the reserved address and size, something like that. We're going to have a look. And remember, this reserved address pointer has to be the pointer that you actually got back from this reserve function, right? It can't be anything else when it comes to releasing, right? So we have to do the free type of release. Now, if you decommit, you can decommit sub pages, but you can't release sub pages. And then returns a bool. I guess the bool means success. Just a guess. I'll confirm that in a second. Return value succeeds. The value is non-zero. Ta-da. Right. So we obviously want to make sure that the size see, I think we can have some layers to this and it can do the assertions in a shared place. But you know. It's not available on the generic Linux kernel, maybe on... Okay, interesting. Right. Just got to replace the Linuxes with the Windowses. Cool. Right, so to commit. So commit, you need to use an alloc. Right, it's like... Okay, no. Within these ones first. So for this one, we will probably want to use mprotect. It's basically the same as calling protection set. Yeah. Man mprotect. Yep. So similar sort of thing. What's the return value? Shall returns it if not. Okay, if it's not equal to 0, error. Excellent. So it's like this, right? But you get your protection like this. You call mprotect addr size prot done. So that's the way we commit on like, because if on every Unix operating system, basically, when you access the page, it auto commits it. There's no explicit commit. So when you reserve, we just make the protection nothing, right? And then when you commit it, we make it so you can actually access it as you wanted. Whereas on Windows, what you want to do is use virtual alloc again, right? But this time you just want to use it with commit. So, oh, wait a minute, we do need these assertions here. And you missed these. Yep, that is very true. So we do want to have this copy. ADDR, ADDR, ADDR. Right, so it must be a multiple of page size. Protection, Windows protection. No reserve this time. The pointer that goes in is ADDR. Right, size, return it to commit with this protection now. And voila. Nice. How do we decommit on the Linuxes? I have one question. If Linux and Windows both are targets, does for low-level ops we rely on the GPU driver? I would recommend to test on Windows while in development, because with Windows 32 API-based memory maps are tricky. Yeah, I know what you mean. I've written this abstraction with comments that outline the differences, and I've written the abstraction in a way to the point where the difference is. So there's a couple of comments that I just have to be aware of, but I do understand what you mean. You can't just freely you can't freely release memory, and also there's something to do with this protection set as well. There's a problem with that. But yeah, I'm pretty aware of the differences. But yeah, I'm not sure you mean in relation to the GPU driver though, because the GPU driver just is the same abstraction basically. I could be wrong, but don't you need to write a byte on Linux to make it commit? Yeah, you don't need to write. You need to read it all right. You just need to access it. So you can just do a read and access it as well. Yep, that's basically correct. Yeah. So decommit is going to be on Linux. We're just going to set the protection to nothing, right? To no access. Prot none. No protection, please. Oh, but we want to use m. There's madvise. Yeah, there's madvise. So we want to use madvise to say don't need expects the time being the application finished with the range, so the kernel can free the resources associated with it after successful don't need the semantics of the memory access in the specified region or change subsequential accesses of the pages in the range will succeed. But the result is either repopulation of concepts, substate concepts. Where's the bit they want? That's not the one I wanted. Where is it? Is it free? Advise free. Application no longer requires pages. Thus frees the pages. Freeing may be delayed. Yeah. For each page marked with freed but not freed, that will be cancelled if the caller writes to the page. If there's no right, the kernel may free the page at any time. Once the page range has been freed, the caller may see zeroed. It's may. That's not the one I wanted. Subsequential is interesting. If you want to ensure the allocs are contiguous in physical memory. Interesting. Yeah. Wait, where's the one that I know about? You know, I can cheat. Where's the past version? Do not need. So it was do not need. Interesting. Let me look at that. Do not need again. Maybe I was reading that wrong. Do not need. Don't expect access in the near future. For the time being, the application is finished with the given range, so the kernel can free resources associated with it. After a successful do not read operation, the semantics of the memory access in the specified region are changed. Subsequential accesses of the pages in the range will succeed, but will result in further repopulation of the memory contents from the up-to-date contents of the underlying maps file for shared file mappings, shared anonymous mappings, or zero field on the one pages for okay, this is okay. So this is applying to what we're saying. So all right. Subsequential pages in the range will succeed, but the result in zero field on demand pages for anonymous private mappings. That is us. Okay, so it is do not need. Documentation. Okay. That function clearly does too many things. Advise. Let's have a look. Do not need. Return. Better be the same return value, right? Yeah, return 0, non-zero for error. Yep. So that's how you decommit on the Linuxes, on the Windowses, as we say it. You want to decommit with the free. So with the free, wait, can I recheck that free return arc? I wasn't quite sure. If it succeeds, the value is non-zero. If it fails, the value is 0. Okay. I remember making that mistake before, actually. Yep. Good. So we want ADDR, cool. We want to say decommit. There's a mem decommit. Yeah, mem decommit. And you can make this at a page level and not just the whole thing you reserved, right? So that's pretty good. Nice. Protection set, so you can change the protection. This might be useful to maybe set no access at certain places in the allocation. Memorize an mmap here. Sweet, I'll take a look. What do you need virtual memory for? So we have low-level access to how memory is allocated from the operating system. So this is the lowest level, and we can just have full control over it for our game. So in our game, the whole idea is we're doing a very simple, like we're trying to like make things as simple as possible. So by having the lowest level access, we can probably like do the most simple thing for our application, basically, right? And rely on assumptions directly from the operating system. Yeah, there's also the will need as well. Yeah. The will need, though, I've heard is not good, and you should do a read instead. And hopefully we'll get to that today so I can show you. But yeah, we have some pros and cons that we laid out, right? Lowest level gives you the most control as a pro. Works on all modern operating systems that we care about. There's neat tricks like the memory is zeroed that you allocate already. You can do some things where you can grow arrays and not have to basically move the pointer to a different place, move the array pointer to a different place, right? You can like grow in place. You can have some like special ring buffer with it, which is pretty interesting. And you can build your own custom allocators on top, so you have control. But there's cons: it doesn't work on embedded systems and WebAssembly, and you have to build your own allocators, right? You have to like the control is a pro and a con, right? And it is probably potentially slow if you overuse it, right? You have to really manage this specifically for your application. You probably answered this earlier in the stream, but why not just use malloc instead of using platform-specific procedures? Well, I probably just answered the question there under closure. Effectively, like malloc uses this system under the hood, right? So we're just using the system malloc uses, right? So we'll be able to define our own custom allocators. Yeah, if you haven't seen this already, let me send you a good link. Ginger Bill custom allocators. When anyone doesn't like know about custom memory allocation and how powerful it is, this is a really good blog, and I highly recommend you just read this blog. So the first one tells you, like, teaches you how to think about different allocation strategies other than just malloc, and how different like lifetimes you can piggyback on different lifetimes of memory allocations and really design a strategy just for that need. So we will be building our own ones like this. But yeah, highly recommend you check it out because it goes over all different types of allocators you can have. Right, memory protection set. So I've already done that. It's basically just the same thing as commit on the Unixes, right? Just the same thing. On Windows, slightly different. There is an memory protect. Just got to use this guy. Wait. Yeah, is everybody? Yep. Right. Basically the same thing as the free, but we'll do with protect, I think. So when we get the prot thing, get the protection, mem protect, ADDR, size, and prot. I think that's it. New protection, old protection. Why did you do this to me? Oh no, it returns the old protection back out. Thank you. Can that be null? If this is null or does not point to a valid variable, the function fails. Thank you. Right, so that's how you do it on the Windowses. So reset. How do you do a reset? Isn't that all my days? All my days. We need to call protection as well, isn't it? Right, so this is the implementation for reset. Do not need. But for the decommit. So for decommit, you do want to give the pages back, so you do advise. But then you probably want to set the protection to prot none. Oh, that was close. Right. So that's do not need, that's the reset. Then on Windows, to reset the address range, so it's like doing a decommit and a commit again. So it gives you back zeroed memory. What's the way I did that? Why do we query? Oh, because we need the protection. Ah. Oh. There must be another way to do this. No, there was a reset, isn't it? Alloc reset. I just remember seeing it. I remember seeing it in the docs. Initiates the data in the specified range to no longer of interest. The pages should be read from. Should not be read from written to paging file. However, the memory block will be used again later and should not be decommitted. The value cannot be used. This value cannot be used with any other value. Nice. Does not guarantee the range member set. Does not guarantee the range will contain zeros. If you want the range to contain zeros, decommit the memory and then recommit it again. Damn it. That's the reason why we didn't do it. So we need to use this thing. So here's one I made earlier. You've got so you use this query thing. It gives you the the information about the memory allocation. So it gives you like the base, reserve pointer, the range. It gives you the protection information. It gives you some other things as well. But we use it just for the protection, right? So we decommit the range, and then we reassign the protection again. And that's all we do. Right. So the final thing that I want to implement is this force physical page allocation. So on every operating system, it does work like this. When you first access the page and you haven't accessed it yet, it will go and get a physical page, even on the Unix operating systems and on Windows. But on Windows, you can't commit more than you have physical RAM. That's the difference. Whereas on the Unix operating systems, you can commit more. You can use mmap and reserve more than you have available in RAM, right, to back it up. So to force the physical page allocation, the reason why we want to do this is because there can be a potential, like I've heard from someone, but I don't know if this is 100% true, so I want to try this out. If you're going to be accessing a page in memory, so you might have virtual memory allocated this many like 4 pages, right? So the idea is, imagine we're going to be accessing this page, and this page, right? we are going to be maybe processing some data in some other memory location somewhere else, bringing that in, right? And sort of like, doing some processing here, and we'll be gradually writing out, doing some processing, writing it out, processing, writing it out. And then we'll hit this page, and then the operating system will be like, crap, there's no page that's been mapped to this thing yet. So it will go out and fetch, it will go and find a physical page for it in the big, in RAM, right? And then you'll do some more processing, go to the next one, do some more processing, go to the next one, more process, and then eventually you get to here, and then the operating system says, hang on a minute, I got to go and get another page, right? So I've heard that the best thing to do is just get this page fetching out the way and over and done with. So when you do this, right, you don't have any interruptions. So the easiest way to do that, there's two ways to do it. You can either write to memory or you can read. So we're just going to read from memory. So the most simple way is just iterate over and do a read, but you have to make sure the compiler doesn't optimize it out. So there'll be a special keyword we use, and so maybe someone can guess that special keyword. You dug into Unreal Engine memory management, haven't reached this level though. They rely on malloc and mi-malloc. Fair play. Not heard of mi-malloc. Can you still use malloc to get backing memory and use it? Yes, you can. But then underneath it will be using this system. But if you're just writing an application, you don't care about doing this, right? You can just use malloc. There is no problem doing that. It's just if you want the control or not, is all. We want the control because we might want to use it for some other things as well. The Stack Overflow said that most people learn programming stuff related to technology through technical documentation. They're popular as blogs. I wonder how true that is. Well, see, I learned it through docs and blogs. So how about books? Where did books come in there, Kappa? For my use case, I just allocate bigger chunks from the OS, manage memory stuff yourself. Yeah. That's the sort of idea we want to go with. The real question is when we are adding the main UC splash screen. Nah. Yeah. Perhaps we can. Yeah, I think we can't do that. Yes, you're right, glorious sir. You have guessed correct. I have no prize, but well done. So we say, probably we want to say like something like that. You know what? ADDR less than. This is a while loop, right? While void endpointer equals core pointer add, because you can't just add to a void star, you have to cast it to integer and whatever, but anyway. C problems, ADDR less than end ADDR. Basically we're just gonna say ADDR equals GOS Linux page size. And now here's the magic sort. Here's the magic volatile. Maybe just an int. Volatile int. P equal ADDR. Dref P. What we're gonna do with it though, int, and then we say core unused v. So we just iterating over each page, and we're just gonna read from the start of the page, right? So you say, so you calculate the end of the address range. We've got some assertions here to make sure it's all aligned to page sizes, right? While that's less than the end address, cool. Get, do a volatile read. You know, we could just cast it into a volatile int, and then just do int v. Just do it in one line. So the compiler shouldn't compile that out, hopefully. And then we put this here so it does an error in the compiler because we haven't used the value. And then we advance the address via the page size and go to the next page, and voila. So we just need to copy that over to the Windows side of things as well, because, you know, we should ideally have it like the GPU side of things, where there's two layers to this operating system thing, right? There's stuff that's shared between the operating systems and more of like a OS backend, right? But yeah. Right, so that is the virtual memory system, and it all compiles on the Linuxes. We can test it out, I guess. Right. So we can go to source main C. We can, you know, we can say OS virtual memory reserve and commit. Well, let's just say reserve. We're going to reserve, let's reserve a page of memory. We get the pointer out, right? So you get the address. So void star ADDR, ADDR. I guess we're going to do a core assert to make sure that's equal to OS result success. Then we're just going to say, I don't know, error. And then we're going to write, well, we're going to write to it and see what happens. So we're going to dref cast it to an int, ADDR equal 5. Now that shouldn't work, right? It should crash. So let's not do anything. But let's just see if it actually reserves. So the game still runs, nice. Now we're going to write to it and it should crash, right? Wait a minute. I've got to recompile it. So there's a segfault, right? And then our segfault handler kicks in and tells us where the exact problem is, line 35. There you go. So that's what segfault is, right? We haven't, we've not got a page mapped to that virtual address space. So now we can say commit. But we can also just say reserve and commit. Right, bear in mind we need a protection now. So this would be OS virtual memory protection. So if we said, let's say read write, right? But we'll, so if we say read write, that'll just work. There you go. But if we said read, it will not work. We get another segfault again. But also you can go back to the reserve and then you say just commit. You can then commit the address and the range with a certain protection of OS protection read write. And then you see me write to that pointer there. And it works, right? But if I made it read only, it does not work. And then, but if I just read from it, let's do a volatile read. Let's read it into A, and then we'll just say core unused A, so we don't get an unused variable thing. Then that'll work. And there you go. So that is virtual memory working, and now we can use this to make custom allocators. Obviously, I've got to get this working on Windows. I think I have to include a header file somewhere. Should we try and chase down that header file? In my allocation solution, I do the same. I just memset 0 on it. Right. Well, use virtual memory, then you memset it? Why would you memset it? There's no point of memsetting if it's virtual memory, though. Think book was 10th most popular, maybe. Okay, wow, fair. Fair play. I always hear people asking about books. But yeah, I think Stack Overflow is not really a good place to figure out, like, all these surveys are all, the data is definitely very, yeah, like, who is the type of person to actually respond to the survey? It's a very small section of programmers. Yeah, I barely end up using Stack Overflow. Most of the time I just lurk, right? And I'm sure that's a lot of people. Can you use stuff, or we can use this stuff, works with LLVM static fake use pointer. Right. Yeah, same sort of thing. But you can just cast it to void, right? That's what we just do, we just cast it to void. Oh, right, fake use. Oh. I think it's still as always since V is not used. Like, if it would... Yeah, I'm not sure. I think it would still do it. I think it still does it. Volatile read. Yeah, because the whole point of a volatile is that the fact that it has to happen. Like, you're doing it, you don't want the compiler to optimize it. And it has to happen in the order you specify it as well. I'm pretty sure that works. But yeah. Right, so we want to find the Windows header for virtual alloc. Is that all in windows.h? Mem API, is that right? Yeah, I think it's memory API. Trying to find the exact include for it. They say it's all lowercase memory API. Okay, let's try that. Include memory API.h. That should be it, hopefully. Or just windows.h, right. Okay, maybe it's already there. How to most stay focused all the time? I don't know, I'm just really excited to get on to the next thing, I think streaming helps. If it's a personal thing that you're doing after work and you want to stay focused, people might think, especially I've heard some people on who make dev stuff on YouTube. I heard them say, well, they get distracted by a Twitch chat, but then it's also like, but do you really stay focused enough when you're not streaming in front of people? So there's a two-way, there's two sides to that coin, right? But yeah. I don't know. I've just also been programming for such a long time now, or long enough, shall we say, where I've been able to notice when I've had bad habits and correct my bad habits, right? It takes a lot of time. Like you have to notice your bad habits and stop yourself from doing it. Like open up YouTube and searching through or whatever, and just really get rid of those bad habits. Yeah. I've been programming for 14 years. 13, 14 years, yes. Cool. Rightio. So what we're going to do is we're going to get this committed to the code base. Git status. Add virtual memory abstraction. Not tested on Windows yet. Okay. Yeah, there's that one. So I'll do that off stream quickly, but if I find anything that's not too obvious, like just fixing some compile errors, then I'll obviously mention it next stream. But I'll give that a bit of a test. So I need to log into the bashes, and I need to do this silly dance, which I've not fixed yet. I don't understand how I fixed this. All right, git push. Oh, there we go. Excellent. So, for those of you who have access to the code, you can go and download it from the repo. Yeah, for those who want access to the code, if you're a Twitch subscriber, go to that link. You can get access to it. But if you want to get access to either sub via Twitch, or there is a Ko-Fi link if you check in the about section below, or on that page, you'll be able to see there's a you'll be able to subscribe via Ko-Fi, then look on that channel on the Discord, and then link up to the GitLab and download the code basically. Hey there, thank you so much for the raid, appreciate it. How did things go? How did the stream go? But yeah, so that was very successful. We've got the virtual memories done. What is next then is we need to get, we kind of want to, we might do a custom memory allocator. And then we probably want to do so we want to do a custom memory allocator and probably make a start on our stack, right? Our array that we have, right? Because we want to have these arrays that we allocate. So I think we want to have a custom allocation strategy. So we might make a linear allocator. I'm not sure what allocators I want to make. I might just start with the linear one. I'll get some ideas though. I don't know, Type Beaver. Maybe because, well, yeah, I don't know. It's too much to catch up on if you're only in too many discords, you know? Right. Yeah. So if people want to follow me on Discord, on Twitter, there's a link there. There's a devlog on YouTube. There's a new one. There's also a VOD channel. VOD. If you're interested in watching the past streams or this stream again from the beginning, it'll be posted there and you can check it all out from the beginning. Awesome. So the next stream will be Thursday, 6:30 p.m. GMT. So basically this time 4 hours ago, but on Thursday. Yeah. And we'll be working on a custom memory allocator, maybe a couple, and then maybe making a start on our custom stack, which is basically an array that grows and shrinks, but it doesn't reallocate. No worries, Goris, sir. Thank you so much for coming. Yeah, thank you so much for coming. And yeah, hope you guys are having a great week and have a good rest of your week as well. Why can't I just get on the thing that I come here for the whole time? Where's my... There we go. That one. Rocket science. Complete rocket science, right? Ah. This guy hangs around in my channel sometimes. Skimmer raid. Alright. You got some CPPs, guys. Enjoy. Hey Vertex, bye. Will you be doing red black tree craziness if you decide to do a free list allocator? No. We're not doing anything like that. Don't worry. We're designing stuff specific for our problems. A free list allocator is more general. But yeah, a red black tree is quite funny to implement. I remember trying to implement one before. It was hard. But yeah. Well, it wasn't hard. It was just a weird thing to read because it's just logic, right? But yeah. Yeah, good to see you, Benny Montana. Yeah, man. No worries, guys. Right, have a good rest of your week, and yeah, enjoy the next stream. I'll see you all on Thursday, hopefully, if not Sunday. But yeah, catch you later.